So can we see galaxy clusters through CMB? Can we, in particular, probe mass of the galaxy cluster using a small-scale CMB effect called lensing? Hello everyone, I'm Sayan, and today I'm going to talk about my work in collaboration with Julia Caron and Louis Legrand in the University of Geneva. So first of all, why do we care? It turns out the abundance of galaxy clusters as a function of mass and redshifts really tells you about the expansion history of the universe. And the lensing signature of these objects are sensitive to the mass of the clusters. And you can study the mass using lensing of galaxies, also using the lensing of CMB. And how it works? When you have a spherically symmetric NFW model or a mass profile in the line of sight of your CMB, it gives you a dipole-like structure in the lensed minus unlensed sky. And the idea is to catch this kind of structure and get the mass out of it. Like any other thing, it has an estimator. It has a minimum variance estimator, which is made of the lensing estimate of the from the observed CMB. Here we use the MAP or maximum A posterior estimator instead of a quadratic estimator, and this makes a significant difference when you think about low noise experiments like CMBS4. But what happens is that it suppresses the noise in the lensing estimate, and as a result it suppresses the noise in the mass estimate as well, and you see 13% improvement in S4 like experiment. To give you a visual sense how the reconstructions becomes better and better, as you can see with our iterative estimator, it becomes better and better, and voila, with the QE it was looking like this, with the map or the our estimator it's looking like this. And that's it. Thanks for listening. Let's catch these clusters.
Hi there, I'm Zach Slepian. I'm an assistant professor at the University of Florida Department of Astronomy. I'd like to use this flash talk to briefly introduce my research group and the work we do. My group is diverse and talented and hardworking, and I'm very grateful to work with them. Across the top row, you see my grad students, several of whom are giving talks at this meeting. In the middle and bottom, several undergraduates I work with, as well as my postdoc and external collaborator, Bob Kahn. So SDSS BOSS has gotten 1 million galaxies. DESI Dark Energy Spectroscopic Instrument will get 30 million. What do we do with this wealth of data? Well, we can search for parity violation in the early universe via the galaxy 4-point function, an idea proposed by myself and my collaborators in October 2021. We can use an excess of tetrahedra over their mirror image to probe parity violation. We use a GPU-accelerated endpoint function code called cadenza, which is so efficient that it can do 2 through 6-point correlation functions. On a single A100 GPU, it can do all of BOSS's 4-point function in 1 minute. And in total, our parity violation search required 7.5 million CPU hours, but that becomes 50,000 GPU hours with our code. So I hope you'll take the opportunity to check out my students' talks. Jess Cellino will talk about the 3 and 4-point function covariance matrix. Matthew Reinhard will talk about axion inflation in a parity-violating 4-point function. And William Ortolá-Leonard will talk about the perturbation theory even parity 4-point function.
Hello everyone, my name is William Ortolá-Leonard, and I am a graduate student at the University of Florida working in constraining the properties of dark energy. To do this, I am modeling the Redshift-Space galaxy 4-point correlation function, and this is what I will be talking about in this video. Just to remind you, the 4PCF is the excess probability of finding 4 galaxies in a specific tetrahedral shape. To model the 4PCF in real space is a difficult task to do, so what cosmologists have done in the past is go to Fourier space where these calculations are a little bit easier to do. What I'm showing you here is the 3-level trispectrum, which is composed of these 2 terms, and this is the base where we start from to go to real space. So what I've done is take the inverse Fourier transform of those 2 3-level trispectrum terms. And so what we end up finding is 17 equations that describe the full 3-level 4-point correlation function in the same format as the one that I'm showing you in here. This is composed of some constants that come from the integration, then also an angular part, and then also some radial integrals in terms of the magnitudes of the vectors R1, R2, and R3. Now, the angular part is expressed in terms of the isotropic basis, which is a combination of 3 spherical harmonics. Here I want to show you some of the results that we found from these radial integrals. And as you can see here, for example, in the leftmost panel is at the integral over 1 spherical vessel times the power spectrum. And as you can see in the top rectangular box, we find that for j equals 0, n equals 0, we find the 2-point correlation function as is expected. Then here we have 2 spherical vessel integrals, 3 spherical vessel integrals, and here a combination of these 2 and 3 spherical vessel integrals.
Hello, so the idea here is to begin with a local structure of four-dimensional space-time, and instead of adding extra dimensions of space, to generalize the expression for proper time itself beyond quadratic order to these higher order forms, and then use the additional components as the basis for matter in that space-time. In terms of the Lorentz group SL2C, this can now be embedded in the Lie groups E6 and E7, acting on cubic and quartic forms for proper time, with symmetry breaking structures that give rise to properties of the standard model of particle physics. In parallel, SL2C can also be embedded in SLPC, acting on pth order form for generalized proper time, giving rise to a hidden gauge sector with suitable properties for dark energy and dark matter candidates, which only interacts gravitationally with the visible standard model sector. I'll say a few words about how a non-compact gauge group can give a candidate for dark energy. Such a gauge group contains both positive and negative kinetic energy states, which can hence be mutually created out of the vacuum via self-interactions, filling the vacuum with these states in a manner which is still macroscopically gravitationally benign due to the symmetric contributions from both the positive and negative energy states. However, there are also matter states of positive energy in this sector, which introduce an asymmetric perturbation, such as it is now possible to get both a positive energy density with a negative pressure in this vacuum state. This vacuum structure then has many of the features desired for dark energy and also derives from a fundamental theory with a well-motivated basis in generalized proper time. Further, if the matter states of positive energy make a much bigger contribution in the very early universe, this could also drive an early inflationary phase with microscopic fluctuations in the production of these states, possibly leaving an imprint in the galactic structure, both in terms of Great Wall or web structures, and also with the production of negative energy states contributing to the formation of voids. So this structure could be tested using techniques analogous to cosmological collider and cosmological bootstrap approaches. Thank you.
Hi, I'm Sayan from Brown University, and my talk today is about limiting dark photons parameters from Jupiter's magnetic field. Dark photon is a hypothetical particle. It can only interact with the standard model through some kinetic mixing with our photon. Since if we have a strong magnetic field like the one generated by Jupiter's dynamo current, parameters of dark photon can be well constrained according to the corresponding dark field. And because we have a precise information of Jupiter's field from the Juno mission, the Jupiter can be a quite potential tool for us to constrain the parameters that we are interested about. Our work have many improvements compared to previous works. The first is our quality of data. The work before just used Pioneer 10, so they only have hundreds of data points because Pioneer just passed by the Jupiter. However, if we use Juno detector, we will have tens of thousands of data points. With this huge amount of data, we can do some detailed statistics considering the error like the fluctuation or the time variation. Another significant improvement goes to much higher multiple model. Previous work only used dipole model, which cannot describe the field properly. As shown in this plot, the high order multiple that we use will include much more details that we want. With this improvement, a much better constraint on the dark photon's mass and kinetic mixing parameters can be given as shown in this plot. In addition, we can also give a better constraint on photon mass with this method as shown at the left-hand side. And this is what we have done in our work. Thank you for your listening.